Pleasure to introduce Ido Schwartz. Good touch. And to introduce Ido Schwartz, who actually was kind enough to travel all the way here from far away Haifa, well, actually beyond the mountains of Haifa. Much appreciated. And Ido is an expert on excitons, which is what he'll tell to us about. I don't think I have anything else to say before we start. I don't know if there's more people that we're waiting for. That's the question. Your computer doesn't have any microphone? Or?
No, it does, of course.
This one. Sorry. Okay, so without further ado,
How do you get rid of this?
what? Oh, click on it, then click on Alt. Fine.
Okay, found it.
Yeah.
Okay, very good. So, good morning. For this morning. And as Hanan like to say, it's not good on the morning.
Late morning?
Yeah, so I'll try to introduce to you a bit about the excitons in two-dimensional materials. Some basic stuff, and then maybe we'll go over to what we can do with excitons. So, it's very long.
No, because it's no. You have to go to the other screen and stop. Stupid thing. Wait. Click X. 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 Look. No. But, wait.
Oh, very good.
I can actually click for you.
Yeah,
Okay, amazing.
very good. Took over the presentation now. So sorry for my technological difficulties. Yeah, so let's go directly to the point. Good morning. Yeah,
Wait, actually, let before this, who actually knows what excitons are?
This was my question. Could say a few words about excitons.
Yeah, don't worry, but who heard the term excitons? Okay. Who doesn't know?
Just from the name, I assume it's quantized excitations.
excitation. Yeah. So yeah, we'll also talk about what is excitation. So we start from there. But before that, I would just tell you a few general stuff and maybe show you some experimental results that will tell us why we need it. Only after that we'll tell what it is. Okay? So even so it's maybe the wrong order, the main issue with exciton, especially in two-dimensional or lower dimensionality, is the most prominent optical signature, okay, in semiconductors. Okay, so this is why excitons are very, very important. Many people work with exciton to study light matter interactions, to study electronic properties, and you can do a lot of things with excitons. In two-dimensional materials, specifically, because of the very thin layers, it becomes even more important than traditional semiconductors. Okay, and we'll see what it is and how we can define exciton, what are the optical signatures of excitons, how they can interact with the environment or probe the environment, if you like. Yeah, and the main thing about exciton is this small plot here. It is a strongly bound electron and hole pair. Okay, so we'll see exactly what it is. Okay, so what happens in two dimensions that is very, very different than three dimension? What happens when we reduce dimensionality? So I guess also Hanan talked about it in the past, but when we reduce dimensionality, we increase interactions, or actually we have a reduced screening between two electrons or electrons and all or whatever. Whatever live in two dimensions have less screening than things that live in three dimensions when we are in material. And this makes the Coulomb interaction, the two particles field, stronger overall. Okay, so dimensionality matters quite a bit to what we can do. Okay, so this I already talked about. We'll start with experimental observation to say, okay, why we need this picture of excitons. We'll define what is exciton. We'll understand what is the difference between 2D and 3D. And a bit of theory. Not too many Hamiltonians, even so Hanan really liked them. But we'll still see one or two. Okay, so regarding experimental observation, so here we can see, actually it's one example of spectra from two-dimensional semiconductor, specifically MOS2.
That's in the TMD category.
TMD. I guess you talked a lot about graphene. This is very, very similar, just it has a bit of band gap and therefore optical conductivity.
Is it actually massively rock?
Yeah, like which is regular band gap when you think about it. Yeah, so what we can say here is that if we start from this figure in the middle, in the x-axis we have energy, and the y-axis is actually the strength of the photoluminescence. Okay, so what these materials emit, how much this material emit light and in what energy.
Maybe explain what photoluminescence is.
Photoluminescence is emission of light. Let's forget about the photo. Let's focus about the luminescence. I will explain photoluminescence in quite later on. Okay, but let's say that this is what this material emit. Okay, so we can think about photoluminescence as, or the emission of light. Usually it comes from the ground state of the Hamiltonian that we can write to the system. Not always. As you can see here, we have more than one line, so it's not necessarily a ground state. But what we can see here in different colors is different layers. How many layers we have in the sample? And in red we have one layer. In yellow we have already 5 layers. Okay, or 6. 6 layers. That's true. Good catch. But this each curve here is actually normalized, and it's normalized by the intensity of this peak. So the A, what calls A, and the A have a meaning. It is A exciton. We'll talk about it later. Okay, but this is the normalization. Without normalization, when we go from one layer to 2 layers, we can see the difference in intensity. If we have the same excitation of the sample, we can see that one layer emit much more than 2 layers.
How we can distinguish between the response of extons and something else with optics? It's like
Well, let me.
I mean, from this plot, you can just say there is an optical transition
yeah,
that's very
exactly.
strong at this frequency.
But why it's actually extons? So
Yeah, so
that's-
we'll discuss this in so this is so the idea of this slide is actually tell us that we have some things that we don't know what they are, or why we need the excitons to describe them. Okay, and when we start, we'll see that we need some other features and normal band theory to describe what we see. But I guess more general maybe is we always need either direct evidence to say that we have something, or some evidence that is supported by theory. And I guess this time it's both. Okay, and it's
So are you going to discuss why the new peaks coming when we have multiple layers? Why these peaks?
I will tell you, but we will not discuss it. So we'll from now on, or after this slide, we will focus on single layer, and we will focus on single layer exactly to avoid this question, which is not difficult, but so we want to keep our exciton theory or discussion simple as far as we can do, and the fact that we see here that we have much lower intensity, and also we have more resonances and even lower energy. Okay, and this is a consequence of when we have 2 layers of the same materials, we have some hybridization of the wave function, the electronic wave function between the layers. And this hybridization can be in different crystallographic momenta. Okay, and we have some momenta or K-space momenta that don't hybridize, some does. Okay, and the difference is that in singular, the minima of the conduction band, the maximum of the valence band sits in the K point. I guess you already know what it is. And this is true only for one layer in TMD. When we go to higher or more layers, depends in which TMD, either the valence band or conduction band or both of them, the minima and maxima of the conduction valence band shift to different positions. Okay, either the gamma point or the Q point. The Q is between the gamma and the K. Okay, and this makes this semiconductor indirect semiconductor if it tells anything. So I will briefly discuss this indirect character later on, but not in the sense of this large, let's say, gamma K separation. Okay. Yeah. So just summarizing this slide, what we can see here is that we have very clear optical spectra. In a moment, we will see that we cannot describe it as a band theory, single particle band theory. And another thing is that we can see that the emission, or both the peak energy and also the amount of emission changing when we add more layers. Okay.
Is it correct to say that there isn't any emission? Like, I mean, it looks like the exciton is a very weak feature. Sorry, this mystery peak is a very weak feature, so you can just ignore the, like, if you're not talking about one layer.
Again.
If you only have one layer, this is a very strong peak.
Yeah.
To the degree where I'm wondering if you can say this is this feature even exists on the 2-3 layers.
Yeah, it's definitely exists, and we'll see exactly why we cannot see this in photoluminescence. We can definitely see this in absorption, however. So the feature exists. The fact that it is not prominent is because photoluminescence also probe dynamics, not only the ground state. Yeah. So moving on. So this is what we discussed. We have the minima of the conduction band, maxima of the valence band. Okay. In TMD, this is, for example, molybdenum disulfide or diselenide. They have similar band structure. We can see that we have here two quantum numbers. One is for the valley, which is the K and K prime, and the other one is for the spin, similar to graphene. A bit low degeneracy, because you don't have the AB site like in graphene. Okay, but you still have two quantum numbers for the spin and for the valley. And what we can also see that in the valence band, and this is single particle picture. Okay, so this is so in the valence band we have very large splitting in the same value between spin up and spin down. Okay, and when we go back to this cartoon, when we say A and B, this labeling, then the A is the spectra that relates to the maximum of the valence band, and the B is spectra that relates to the lower energy of the valence band.
So one A is for the spin up and B is for the spin down?
It depends in the valley.
Okay.
Yeah, so it's both spins and both valleys.
Yeah, but it's symmetric, right?
Yeah.
If I
So, you have your time reversal and
Yeah.
this is symmetric. Yeah. Okay, so this is the definition, and the energy difference is a few hundred milli-electron volt, like 0.2 electron volt. Okay. So again, the photoluminescence will probe mostly the ground state. Okay. In the conduction band, we have different story. We also have splitting. We have spin orbit coupling. We have splitting, but the splitting is small. And depends in the TMD. It could be either negative or positive. That means that either the spin up is lower in energy for MO and whatever you put after, whatever calculation you put after, the splitting will be negative. If you have tungsten, it will reverse, and that will have consequences for the emission later on. We'll discuss it. Okay, and if you look on the entire band calculation, you can see the splitting in the valence band, and in the conduction band it's quite small.
How
Okay.
small?
Below 30 milli-electron volt. It's not small compared to gallium arsenide, for example. It's much smaller compared to the valence band splitting. It's order of magnitude weaker.
Is it measurable in experiments? This gap?
Yes. Yeah. Well,
No,
this splitting is easy.
Yeah.
You can immediately see it.
No,
Also this one
I
is
meant for the
measurable.
balance.
Yeah. Also the conduction is measurable.
Wow.
Okay, and it's measurable when you understand what happened in photoluminescence, at least in the case, not in this case, where you have this splitting, but in the other configuration, it can easily be measured directly in photoluminescence. Okay, so after we've seen this spectra, even so we discussed too much without explaining so far, let's go one step back and look about the what we expect from single particle picture. Okay, and if we have single particle picture and we have a three-dimensional semiconductor, we should expect that we have no density of state. So the y-axis is optical absorption, and we expect to have optical absorption when we have density of state to promote electron from the valence band to the conduction band. Okay, where we don't have states available, we cannot promote electron. Okay, so for that we need some density of state, and the single particle band theory says that the optical absorption will follow the density of state of the material. Okay, and this actually happens. Okay, so we have some absorption between different bands. Okay, and it could be quite significant. Yeah.
In 3D, you don't have a bound of singularity, typically speaking. I mean, in both cases, you'll have, because the band is flat, you'll have some sort of singularity, but in 2D, it should be a sharp step, like you show below, but in the top one, you should have a spike, no?
It could be. I'm not certain, but it could be.
Okay.
Really not certain.
Okay.
In sense of.
Like in band theory, in principle, you can only have unhooked singularities in 3D. So, I mean, not sure what. Maybe it's like an indirect band gap, or
No, this is for direct. It could be that in the optical absorption you have
Okay.
usually you have maximal absorption in the
it's
band.
optical absorption. Yeah, then saying the density of states will have a peak anyway.
Yeah, so we will also have a bit of, but it will not be very large. And anyway, it will not be very large. Okay, so this is the 3D density of state, which goes as a square root of the energy above the conduction band. And in 2D, when we have parabolic, all of this assuming parabolic dispersion. And 2D, we have a step function. Okay, so we expect in the single particle picture to have no absorption and then step function in absorption when the energy go above the gap. However, we don't see either of these pictures. Okay, so in the one layer we see single resonance. We don't see any step function. Okay, and this is 2D LED. Okay, so and when you think why we need different description, this is the first thing that come in mind. Okay, the absorption or emission does not follow the single particle picture. Okay, another thing
is the fact that you don't have the splitting also spin orbit.
Well, you have the splitting. Well, you see it. This is in absorption. You will see.
Okay.
In PL, it's a bit more
okay.
Difficult. Okay. Yeah. So, as we say, we have some differences in the spectra compared to the single particle picture, and the optical gap does not match the band gap of the material. Okay, so the energy of the optical gap or the optical transition is lower than the band gap of the material. Okay, it's not unique to TMD. It's every material that have optical transition, or almost every. Okay, so now we can start discussing what is exciton. So this is what we wanted to define. Okay, so an exciton is a correlated state of electron hole pair. Okay, and I think it's very easy to get intuition from this kind of picture, or this kind of picture. Okay, when we the photoluminescence, we shine light, we promote one electron from the conduction band to the valence band. Okay, and now in the valence band we have a place where we don't have any electron. Okay, and you can think about it. Now we have interaction of the electron in the conduction band. Okay, we still have the same amount of electrons in the material. It just one electron have different energy. Okay, it occupies different orbital. Okay, but now we have the rest of the electrons in the valence band. Okay, that interact with these electrons. We have this Coulomb repulsion. Okay, so the place of this missing electron in the valence band will want to follow the electron in the conduction band, if we talk about spatial coordinates. Okay, think about it, that this electron now moves aside. In this region we have more electrons, we have more repulsion. Okay, so overall what we have, it's actually we have some binding energy. Okay, when the electron sits on top of the missing electron in the valence band, we have lower energy. Okay, than the single particle picture. Okay, the single particle picture tells us, okay, if the valence band is full, let's say, then we have one more electron. What would be its energy? Okay, so it's different story. We don't have one more electron now. We just have the same amount of electrons, only one electron occupy different orbital. Okay, so overall this electron hole pair wants to move together.
Can I ask you something about the? It's related to the previous slide actually. So. No, yeah. So if the optical gap is not, so what does it mean that when a photon hits an electron and promote it to the next level, then and it's not equivalent? So where does the electron gets energy from, if not from the photon?
No, it gets energy from the photon, but the amount of energy does not equal to the gap energy. It's a bit lower.
So
and it is lower because you don't add another electron, you rather just change one electron orbital.
yeah. So how it gets to this energy level? I mean,
Why this energy level and not other? Or
no. So you have an electron in the valence band, and now you give him a photon energy, which is not equivalent to the energy that he needs to get in order to get into the valence band. Okay, a little bit lower.
Let me give you another intuitive example. It's not exactly the same, but let's say that you have a hydrogen atom with the electron in the s orbital, and you want to promote it to the p orbital.
Mhm.
Now you apply magnetic field. Okay, and the magnetic field, it's another term in the Hamiltonian. It changed both the energy levels. So now the photon that you need to, or the resonance energy, changed. Okay, according to the external field that you applied.
Yeah.
Okay, and you have to match the photon energy to this external field. If you use the same energy as without the field, there is no resonance. You'll do nothing.
Yes.
Okay. Now you can also think about the. It's a simplified picture, but think about it that all of these electrons actually generate electric field. Not magnetic, but electric field. Or some Coulomb interaction, the Paschen interaction.
Mm-hmm.
Okay, so it's another term in the Hamiltonian.
Okay. So you're saying that the Coulomb interaction is what is the missing delta for the resonance?
Yeah, it's a huge delta in TMD, but yes, exactly. So the Coulomb interaction is what gives you the lower energy for the photon, or for the optical absorption or emission. Okay, so yeah, just about. Okay, yeah.
How can the hole leave the valence band exactly?
The hole is in the valence band. The hole is in the valence band, but maybe also this is a kind of intuitive picture when we see the electron and hole moves around, because in this picture they are plane waves, so they live everywhere. But let's assume that the center of mass coordinate move. Of this electron moves, it will just drag
Oh, I see.
the hole
I see. The
with it.
pairs form basically create something that's in between the two. Okay, I understand.
The what?
The exciton, I understand.
Well, the exciton is just electron hole with some Coulomb interaction.
Yeah, with the Coulomb. Okay, I understand.
Is it important to distinguish between a single particle? I mean, you can talk about like a single. You're not adding an electron. You're making this point that you're only changing the orbital. Or you can also think about it. You added an electron, and then because of Coulomb interaction, it kind of reduced its energy a bit.
Yeah, but how you reduce the energy?
Interaction with the hole.
Yeah, okay. So this comes to a different question. How you generate this electron hole pair? So you can add the electron, but then to get this Coulomb interaction, which is not let's say constant, with our dynamics is you need to get the all. Because if all the electronic states are occupied, you will not see. So you need to have some missing state, missing occupied state in the balance band for that.
Sure.
Yeah.
Is there a chance to have also connect another electron or another pole to the spares, or just?
Of course. It's what makes it very, very nice.
So you will not have exciton, you will have something else, right? Or
Yeah. We'll go to there maybe, if time allows. Yeah, so this what will make this very, very, very nice to do things similar to what you're doing in your lab, actually, just using optics. Okay, so now we can say that we have electron and hole, okay, which are correlated or having some binding energy because of Coulomb interaction. And if we look about it in real space, we can say that we have it's very similar to hydrogen atom. So we have some positive particle, the hole. We have the negative particle. Okay, this is a bit misleading picture because it's not the electron orbit the hole, like in hydrogen atom. And this is well, in hydrogen atom we have the proton as a positive particle, and the mass ratio between the proton and the electron is huge. So we treat it as if the proton doesn't move at all, only the electron orbit. But actually, if we have almost equal masses or the same order of magnitude of masses, these two bodies or two entities circle each other. Okay, so this picture is a bit misleading. It's more like a hydrogen atom, but other than that, it's very, very similar. And what is also slight different now from hydrogen is that because we live in material, we need effective mass, and we need to adjust the Coulomb interaction because of the material or polarizability. Even so, I will not go into it. We can see that in this very simple schematic, this entity lives on many atoms. So it spreads over many atoms. So this is called Vanir exciton. Okay, that the crystallographic registry doesn't really affect the overall wave function. It's like the Bloch function from the band theory and not the atomic wave function. Okay, and we have another kind of exciton which is localized around the single atom, which calls Frankel exciton. But this, let's forget about it and focus only on the Vanir exciton, like this picture. Okay, so two differences from right now from hydrogen: effective mass instead of mass. Okay, and the Coulomb interaction is screened by the material or polarizability of the material.
But in this picture, the one who circles is the electron, and the one who is in position is the hole. It's not the opposite.
Well, this is exactly what I tell. They actually circle each other. So you can think about it as a point of view. If you sit on the hole, the electron circle the hole. If you sit on the electron, okay.
Yeah.
So from our perspective, the sun orbits the Earth. Yeah. So this is exactly the same. the main difference, for example, between hydrogen atom, which is proton, electron, Earth, and Sun, is the huge difference between the mass. Here, both the electron and the hole have more or less the same mass. So these two entities really circle each other. So if you look from outside, it's not one entity circle the other.
Yeah.
Both of them moves.
First of all, you say they have similar masses. That could be the case, but like because of the spin-over coupling, you can see that the bands are not like the conduction and valence band are not really mirroring each other. So the masses are maybe similar, but they're not identical.
They are not identical, but
Okay.
they are up to 20%. So they're quite similar and quite heavy, actually. So in TMDs, the effective mass is about between 0.6 to 0.8 of the electron mass. So in gallium arsenide, it's in the conduction of 0.05 ME, and in the valence band is a bit heavier, about 0.5.
In bilayer graphene, anybody remembers?
Graphene is lighter.
Yeah.
Much lighter.
So in bilayer graphene, it's like 1/30 of the electron mass. But why is the distinction between the Frankel and the one-year exciton actually important?
I guess it's mostly to how you solve or what Hamiltonian is like, because Frankel you have to take into account the atomic orbitals.
Yeah.
Therefore, we don't like them. Yeah. Okay. So let's move on to try to describe a bit the exciton, and this will be one of the, I guess, if I remember correctly, only one of the two Hamiltonians that we will see here. So the first thing, as we said before, we'll use effective mass, and the effective mass, like in graphene or other solid state places, relates to the band curvature. Okay, and when we work about the band minima, we can approximate everything except for graphene to parabola. Okay, and this will set the effective mass. So this is the definition of the effective mass, and if we just want to look on the dispersion, we have some energy, constant energy, which, let's say, if it is in the conduction band, is gap energy, and some kinetic term that depends in the effective mass. Okay, so it's the same picture. Okay. Okay, and again, if we write the Hamiltonian, as it is written here, it actually looks exactly as the hydrogen Hamiltonian. Okay, because we didn't plug any number except for the effective mass. So in the hydrogen, you will have the proton mass and the electron mass. Usually we can neglect one of them. Okay, but we actually don't need to. And we have some Coulomb potential that depends in the distance between the electron and the hole. Okay. In this case, because we don't have one mass which is much larger than the other mass, we cannot discard one of the term. Okay, we just change variables. Okay, we want to separate this problem to look on the center of mass motion of the exciton and the relative motion between the electron and hole. Okay, so we can think about it that we'll have some entity that moves with center of mass motion and some internal structure inside. Okay, so this is the idea. Okay, and this change of variables, we define new center of mass coordinate and relative coordinate, and this will give us also the total mass, electron plus all, and the reduced mass. So these are the new variables. Okay, and after we put this to the same Hamiltonian, this is the wrong computer.
What? Which one? This one?
This one. Okay. After we put this change the variables to the Hamiltonian, we get this new form of the Hamiltonian. Okay, where we can see two terms that relates to the relative motion. Okay, and one term that relates to the center of mass. Okay, and then we can use ansatz to
Can you check that you're recording?
again.
Can you verify that you are recording? Like in Zoom. Zoom or something.
No, it's
Yes, I suddenly noticed that. Okay, keep talking, I'll.
yeah.
Yes. Okay, I remind you this talk is not recorded.
That's for YouTube.
Yeah. Anyway. How do you make it disappear?
Click Alt now. Again. Wait, no.
Just
Click
let's see.
anywhere and
Give me your mouse back.
Oh, very good.
Click Alt. Once. Okay.
Very good. Okay. So after this, okay. So we change variables. Now we have this kind of Hamiltonian, and we can say, okay, the overall wave function is separable. We can separate the center of mass motion. This is this e to the I q r, which is q, the center of mass momenta of the exciton, and we have some wave function that relate to the relative coordinate. We still don't solve this. Okay, this is general. It's also true for the hydrogen atom. Okay, so if we plug in back this ansatz, we can get only the relative coordinate wave function. Okay, if we plug it into the Schrödinger equation. Okay, and this equation we have to solve. Okay?
Questions?
Questions? So overall, if we just remember, we need to remember this describes exciton in material. Okay, it still can be 2D, 3D, 1D, whatever. Okay, and the overall energy of the exciton after we do this, we'll have this term that relates to the center of mass. Okay, which is just the momenta as any particle, and we'll have some energy that relates to the relative motion, so to the internal structure of this exciton.
Right. So but you don't know what EN is.
Not yet.
Okay.
This relates to a lot of parameters.
But it's not just periodic, like Brillouin zone.
No. So the center of mass, this is the Brillouin zone part. Okay, so this is the crystal momenta. okay, of the entire exciton. We'll see that we can deal with the exciton as a rigid body, okay, because the center of mass need to move, and the electron and hole can move around it, but they have to move together. Okay. So this is relates to the crystal momenta. This is relates to the internal structure. What orbital the electron and hole occupy. Okay. But this is very, very general. So this is still exactly how the hydrogen atom looks like. Okay, so if we take kinetic energy of the hydrogen atom, this is this term. And this is the rest. This is what you actually solve, usually, for the hydrogen atom. Okay. In 3D, let's now try to see what are the differences between 3D, 2D, and what are the consequences, and actually solve for psi. Okay? So in 3D, the potential that we have, maybe I should have the right. We still, what we didn't define yet is this potential. Okay? Because we didn't define it, we until now everything is general, very, very general. Okay? Now if we go to define this potential, this defines the internal structure of our electron hole pair. Okay, so in 3D, the potential actually looks like the Coulomb potential, only with one small difference. Okay, it is reduced by the dielectric constant of the material. Okay, but other than that, it's exactly the same. Okay, so what we can expect when we solve it in 3D is that we'll get the same structure as hydrogen. Okay, the same orbitals. Okay, so nothing special happens. We have two differences: effective mass, reduced Coulomb interaction. That's it. Okay, question? What happens when we go to 2D in materials?
So you're making it like sounds very easy to, especially the Coulomb interaction. I mean, if it's screened, it's like very different potential than what you wrote here.
No, well, depends how you scan it. If it's isotropic and still goes as 1 over r, if it still goes as 1 over r, it's the same.
Usually it would go like a Thomas Fermi screening where you have like this, where you have basically like you know 1 over q plus qtf kind of terms.
QTF?
Thomas Fermi, the Thomas Fermi screening wavelength. Where basically what you'll see is that you don't have any screening past a certain length scale. You don't have, sorry, you don't have any interaction past a certain length scale because of screening.
Well, okay. But this length scale is, okay, it relates, later on you can check what is the length scale compared to the distance within your particles. So as long as this length scale is much longer,
Okay.
and it is much longer, at least in 2D, in these materials.
Okay. So you're not actually screened. So it's,
No,
there's no problem.
it's screened, but not as, it still goes 1 over r,
Okay.
relatively short length scales. So we should think about it that the distance between the electron and hole is a few nanometers. Also in materials, and this length scale we still have significant Coulomb interactions. Actually, at at least to 1 or 2 order of magnitude larger distances. Okay. So, what happens when we go to 2D? When we go to 2D, we have a weaker screening. Okay. This comes. You can think about the polarizability in 2D is only 2-dimensional. Electric field is still 3-dimensional. Okay, so if you have electric field lines that go from this 2D slab, okay, it is not screened. Okay, the electric response is not local, and that means that we have some frequency dependencies, actually. And the interaction deviates from 1 over r in short wavelengths, short scales. And therefore, instead of defining this screening by the dielectric constant, we need a different quantity, and we'll do that with this characteristic lengths are known. Okay, and this will come to separate between short distance to long distance. Okay. Later on. And what we said about the screening, we can see that if electric field lines goes outside the slab, they are not screened. Or the screening is different. Okay, and okay. So now we come to how we model this 2D potential, and we model it by the Keldysh potential, and the idea of this potential, you can forget about the H0 and Y0, which is the Struve and Bessel functions. This is not the issue. The issue is there are two things about it. One thing is what happened in short distances. What is the in the limit when the distance between the electron and hole goes to 0, and what happens in very large distances. Okay, and in very large distances, we go back to the normal 1 over r screening. Oh, okay, so here I've plotted this short distance and long distance. Okay, so it's actually the difference between H0 and Y0. Okay, the Struve and Bessel, or the combination of the two. The green is 1 over r. Okay. The small x is the Bessel function, which is the nominal part in small distances. Okay, in long part it is a Struve. And what we see is that we have, at long distances, we have the 1 over r of the Keldysh. This is the blue line. In small distances, this is logarithmic scale. We see that this potential is so much smaller than the 1 over r. Okay, so essentially we have no screening in short distances. Okay, so this potential just smoothly make the transition between no screening at all at short distances to 1 over r screening at large distances. Okay, and what set the transition point is more or less r naught. R0. Okay, so this is the new length scale between the two. Okay, and why we need it? We need it because when we go to calculate and measure the different orbitals in 2D, they does not fit hydrogenic series. Okay, so we need some other potential to describe the problem, another model. Okay, and this model works pretty well. Another thing which is important, maybe we'll see it in a few slides, is that we need enough orbitals in order to even appreciate this difference. So if you have only the 1s or 2s, it's not enough to say if 1 over r is good or not. Okay. So, just to conclude, if we have three-dimensional material, the Coulomb potential will go as 1 over r, at least for the exciton in this length scale. And the energy levels will go 1 over n squared, which is a principal quantum number, like in hydrogen atom. Okay? Just different constants. In 2D, we have modified interaction at short length scales, okay, or no interaction at all actually. Because of that, we'll get strong binding energies, or stronger than if we have the skin potential, and the level spacing will not be like hydrogen anymore. Just a question: if we go to IN, would the energy separation will still go as 1 over n or different for n? Let's say n equal 10 or 20.
Will be different.
N equal 10 or 20, it will
No,
go.
it should be as a Coulomb potential. It's because
Exactly.
it's large. It's large
will-
distances.
Exactly. So if you have IN, it will merge back to hydrogen series. Okay, because see the potential go back to 1 over r when we have large orbital. Okay, so if we go to large principal number, the orbital is much larger. So the distance, the average distance between the electron and the hole become large. Okay, so we expect actually if we get higher in the principal number that it will go back to resemble hydrogen.
Sorry, it should be the other way around, right? If you have a very large distance and you see strong discrete Coulomb interaction, then
Yeah,
it's exponentially decaying essentially.
Well, you see strong screening, but it's still the same as hydrogen screening, just different constants. It goes like 1 over r.
Then it's not screened. If it like the 1 over r is
No,
the
it's
unscreened.
screened. It's screened. So the scanning will come from the skin, but in different way.
Okay.
So you anyway you have the skinning. In material you have the skinning. It's only the what matters is the shape of the skinning. Okay, how the Coulomb interaction reduce with the distance. Now you can see nice figures if you're not sleeping. Yeah, so this is more or less, let's say, this slide more or less summarize what we've seen so far. So what we can see in this slide is, first of all, here we have the optical absorption, which will relate, we can relate to the excitonic wave function now, or at least partially. Here we can see the two-dimensional band gap, and we can see that we have below, or in lower energy, we have the excitonic resonance. So n equal 1, 2, 3. So we have a series of resonances that relates to the principal quantum number. Okay, specifically to the 1s, 2s, 3s excitons. Okay, and they come below the band gap. Okay, after the band gap, you also have absorption due to the regular absorption with the band edge of the single particle picture, as before. So this is schematic.
So this is the 2D, right? The line.
Well, yeah.
It's like-
This is 2D. The difference between this
No. When you are where it's written free particle band gap, now it's matches the band gap theory, right? Of one particle.
yeah. So
Because
So the free particle band gap, you see, it's here. It's not this arrow. This is the binding energy.
yes,
This is the free particle band gap. Okay, all of this.
yeah.
Okay, and the difference between the single particle band gap and this excitonic state is actually the binding energy. How strong the electrons is attracted to the hole.
But how is possible that the optical absorption of an n equal 1 is larger than the optical absorption of a free particle? What is the intuition behind?
Well, the intuition that you have much larger density of states for that. So because when you generate using a photon, when you generate this exciton or electron hole pair using a photon, you generate them in the same place. So they immediately feel the Coulomb interaction.
Okay.
Okay, in order that they will not feel the Coulomb interaction, okay, some part of, you can say they escape, but they need some separation. Okay, or in other words, when they don't feel the Coulomb interaction, they are already in the, let's say, very high principal quantum number, that they are actually free to move around. But they are not correlated anymore.
Yeah. Oh, okay.
Okay, so in a sense, it's like excite the hydrogen atom above 13.6 electron volt. So you just don't have specific resonance anymore. So you are in a continuum of states. So all of the principal numbers are so much packed together that it's actually a continuum.
Would be a good point to stop for a break.
No, they don't think so. Yeah, let's stop. אז עצרנו עם אקסיטונים, שם גם התחלנו, ואמרנו שהאינטראקציה משתנה כשאנחנו עוברים מתלת מימד לדו-ממד, ודיברנו על זה, ואם אנחנו מסתכלים על דאטה שאנשים מדדו, אז אנחנו רואים, זה ניסוי של absorption, של איפה יש לנו פליאה. אז אנחנו רואים פה את ה-1s state של האקסיטון, אוקיי, ורואים את כל ה-Rydberg series. כן.
We discussed about it during the break, and I had a question. I think the screening is from the other electrons in the valence band, right? I mean,
Yeah, the screen is from the electrons, and we can also say protons. It depends. It's whatever lives in the crystal.
So the
So it's
electron.
usually the polarization of the electron.
Okay.
Yeah. So sorry, I switched to Hebrew before, but anyway, we can see the Rydberg series here, and when we plot in red, this is the hydrogen series, like energy separation between the excitons, and in blue is the experimental data, and the triangles are this modified Keldysh potential. Okay, so we can really see that we deviate from this hydrogenic series. Okay, so here we stopped 4, and now let's connect this also to a bit to light somehow. Okay. And we should also remember that when we talk about resonances and absorption or interaction between light and matter, or at least in absorption, we need to also conserve momenta. Okay, so this is also very, very important when we talked about excitons in solids in general, because the momenta that light carries is very, very, very small compared to the crystal momentum. Okay, and we can more or less estimate what is the difference between the light momentum and to the one or the first frequency of momentum. Okay, so the momentum edge, and let's say just plug in numbers that we have wavelengths of 1 micrometer for the light, which is near IR. Okay, visible is half micrometer, this range, and the atomic separation is in the range of 1 nanometer or even less. So we can tell that the photon momenta is about in this range 1/1000 of the Brillouin zone. Okay, so just back of the number. Obviously, it depends in the photon wavelength. So if you go to shorter or larger wavelengths, it changes quite a bit. If you go to X-ray, it will be already similar to the crystal momentum. Okay, but when we talk about visible frequencies or near IR, the photon actually carry almost zero momentum ביחס, compared to the brilliant. This was funny. See. Okay, and
Recording? Is it recording now?
yes.
So everybody will remember his biyachas instead
Yeah.
for all the times.
It would be in the exam.
Yes. By the way, there's an exam. But that's the only question in the exam, so you don't have to be worried.
Yeah. So anyway, we can treat that the absorption is almost or around the Q, the equals 0. The center of mass momentum equals 0. Okay. So this is a very, very important.
But if it's Q equals 0, so it means that they are highly unlocalized, right?
Well, no, it means that.
And then
Well, you mix two different things. The Q equals 0 is where you have the possibility to conserve momenta when you absorb light. It does not tell you what is the excitonic eigenstate, which is much larger. Okay, so the excitonic dispersion is way larger than the
So Q-
momenta that interact with light.
So Q is actually the momenta of the center of mass.
So we have the center of mass momenta, which is large. Then we also have another thing which is very important, is that we actually generate the electron and hole in the same spatial coordinate. Okay, so in that sense, the oscillator strength is relative to the relative wave function at r equals 0. Okay, if the electron and hole are separated by large distance, we cannot promote one electron from one place to a different place. Okay, so this is another thing. So we can have finite, small, very, very small finite center of mass momentum, but we cannot have relative motion when we generate this. So, okay, so the all that we leave behind have the same moment of the electron that we took, or opposite quantum numbers. Okay, so the oscillator strength is actually relates to the relative wave function at r equals 0, and that means that we also don't have any probability to absorb light if we have high angular momentum states, like the p orbitals or d orbitals, whatever. Okay, we must have finite probability at r equals 0. Okay, and that also tells us that if we go from 1s, 2s, 3s, then the spatial distribution, the wave function become larger. Okay, and therefore the portion at r equals 0 becomes smaller. Okay, and so the 1s exciton have higher oscillator strengths, and it reduces when we get to higher principal number. Okay, so this is more or less what we just said. Okay, and this is why we also see here that the peaks have a smaller absorption. Okay, photoluminescence. Now we go back to where we started. So we started by looking at photoluminescence, and photoluminescence is a process where we have luminescence that was generated by photons. Okay, so we shine light on sample and we get light back. What kind of light? Different than what we use to excite the sample or shine on the sample. So in photoluminescence, we usually excite high energy states. It could be either in the in one of the band, like promote one electron from the valence band either to higher state in the conduction band, not to the ground state, or even higher bands. Okay, that's matter. Okay, the main point is that we have higher energy to excite the sample. After we have this higher energy, the electron and hole relax to the ground state usually, okay, and emit light. But this is very, very important difference than absorption. Okay, because the absorption tells us a lot of information about the optical transition itself, initial state, final state, whatever. Photoluminescence, however, because you have this very fast relaxation, usually it's picosecond time scales, also includes dynamics. Okay, and the probabilistic distribution of this exciton into different excitonic states For example, if we have higher temperature or whatever. So exciton will decay in very cold temperature to the ground state. If we have elevated temperature, not necessarily to the ground state. When we have phonons and we have other processes to scatter the exciton to higher states.
So if I'm trying to figure out, like, you're describing this relaxation, but like it happens both for the electrons and the holes.
Yeah.
But if the electrons and the holes are sitting on different like split bands because of the spin-orbit coupling, can they relax? Like, can they?
Yeah, I understand the question. So the question
Please
is, we
explain
have
it to everyone. Yeah.
all or electron will spin up and electron will spin down. Can somehow the all can flip the spin and then you have emission or something similar? Can we scatter different kind of spins or different kind of valleys? Or yes,
Because you have spin-orbit coupling, so it's like the lowest energy state is not will have opposite spins.
yeah. So in pristine sample and zero temperature, probably not. But if you have impurities, either magnetic, and if you have more than one excitation, so two excitons can interact with each other, or exciton can interact with electrons, or with whatever, as long as we have open channels to scattering, usually the excitation will go to the ground state in cold temperature. In higher temperature, obviously we have other channels. You have phonons to scatter.
Yeah, so just to understand things, it's like at the first you came with the light and you combine electron and hole as a pair which is called exciton, and after some time this pairs just decay and do some recombination and just release photon energy, right?
Yeah, but the all is not decaying.
No, it's like the pair
Well,
itself.
the all
I mean,
it's
the all
not
is
decay. It's go to the minimal energy state.
Mhm.
So the electron goes down in energy. The all goes up in energy because the all is
it depends from where you took the electron, but basically the all is just annihilated eventually.
well, we have recombination. We call it.
Recombination,
So the
okay.
electron go back to its place and emit photon. So
Yeah.
we can have other processes.
Yeah.
Usually it's not interband. Okay.
Yeah,
so
it's
So when we talk about interband, so transition between two bands, usually we do it with photons.
Yeah.
Intraband, a lot of time we do it with phonons. Okay, so it's just matter of energy scale. So
So-
photon can take much more. Well, also phonon can take a lot of energy, but it's not probable. Extremely not probable.
So your excitons has a specific lifetime, right?
Yes.
And it's very short.
Well, pretty short or not, this depends in a lot of factors. It depends in the photonic environment or the photonic density of states. The initial light matter interaction, the size of the excitonic state itself, the dimensionality. So a lot of factors. And the kind of exciton. We see that we also have dark excitons that have extremely long lifetimes. Right? Okay. But the main idea here is that we generate these excitations using photons. So we generate correlated electron hole pair at some energy. This energy is very large with zero momentum. In order that this exciton will relax to the ground state, it needs to scatter. While scattering, usually we also give and take momentum. So this relaxation, usually it's with phonons or scattering with impurities or impurities. And so eventually, it depends in the excess energy that we give to this exciton. We might eventually start with one exciton that was dissociated because we gave it so much energy. Let's say more energy than the binding energy, and then the electron and all are moving around because they have so much energy, and they come back with different electron volt pair to end up. It's also a plausible situation if you have a lot of excitations. If you have very few excitations, then if you dissociate the electron and hole, the probability that they will find another particle to play with is very, very small. Okay, so this is the process, more or less the process of photoluminescence, and we have this competing mechanism. So we have the relaxation and we have the lifetime, which is faster. Okay, so this will tell you from which states you will see light. Usually, relaxation is faster than the lifetime. So usually you will see more light emitted from the ground states, or from states from which relaxation must be quantized. Okay, so because if you have quantized relaxation, usually it's slower. Okay, you have less phonons, for example, to scatter, to take the energy. And okay, so and this will give you also different signatures in photoluminescence and absorption. And this is one thing. Another thing, the difference is absorption. You start from ground state and you go to excited state. Okay, with photoluminescence, you start from excited state and you go to ground state. Okay, you can actually see different optical transitions if you look at these two processes. Sometimes, not always. Okay, so after we talked about exciton and how they interact with light, let's talk how they don't interact with light.
So wait, maybe like for the experimentalists, when do you want to look at PL? When do you want to look at absorption? And when is the signal larger from each?
Well, for example, when you want to look on dark states, or what you initially think it's dark state, you want to look on PL. Or when the oscillator strength is small, you want to look on PL. If you want to go to the regime of single photon or few photon emission, you also want PL.
Emission.
Yeah, well, you can also do single photon from laser reflection. It's still one atom or one entity that can scatter one photon at a time.
Okay.
But for that, you need cross polarization to distinguish this photon from the laser photon. Yeah, so it really depends what you want to observe and what your goal.
And when do you want to absorption then?
When you want absorption, when you want to look on higher states, you want absorption. A lot of time you don't see emission from PL from excited states. If you want to probe your environment in a clean way without this dynamics and a lot of heat, a lot of time you want absorption. But it really depends in the purpose. Okay, so after we talked about the interaction of these excitons with light, this is mainly what we did so far. We can separate the exciton in two kinds: bright exciton and dark exciton, as usually on the two things. So the bright exciton are optically allowed. They can have radiative recombination. This is the PL, and they are visible both in absorption and PL. In PL, only if the state leaves enough time to emit light. Dark exciton, however, they are optically forbidden. So there is some conservation law that forbid this transition for some reason. and they have either weak or no direct emission. So this we talk about PL. A lot of time we can see emission from dark states in PL. Okay, it could be orders of magnitude weaker than the allowed position. But eventually, when some excitation live long enough and it has some finite probability through scattering with either phonon impurities or tiny wave function overlap between the electron and all, then it will eventually emit light. Okay, but it can take much longer.
So it's become bright exciton, right?
No, it's
Or
called
still
dark
dark.
exciton. If you take allowed transition, and which let's say that the also strengths of 1, and the dark state usually will start with 1,000 times weaker interaction with light. So the also strengths 1,000 times weaker or even more. Okay, so it just tells that you have some other mechanism that can scatter the electron and all to the right place that eventually they will emit light somehow. Especially in solids, that we know that we have a lot of impurities and a lot of other things that can scatter, then usually states are not completely dark. Eventually they will emit light.
Can you also get Raman signal from optical, especially bright excitons?
Yes. Yeah. So the question the question is what you call Raman. So if you just
Like the nonlinear process where you have.
well,
Yeah.
this you can get EAT or whatever if for that you call Raman. Yes. Depends what kind of Raman you're referring to. Okay. Yeah, but I guess just excite phonons. You can excite phonons, so you can see emission, lower emission. Let's say if you have optical phonon, you can see lower emission lines. So you can see the series of one optical phonon, two optical phonons. Depends. You need to design the sample good enough. Absorption of phonon is much more difficult. Okay, so what is important with dark excitons is that even that they don't emit light or very weak emission, they can still be most of the excitonic population in the sample. So the fact that you don't see the exciton doesn't mean that they are not there. And it also doesn't mean that they are not influence other properties of the sample. Okay? So they have some significance in that sense. So we also have few kinds of dark excitons. For example, spin forbidden. So if you took electron from the valence band to the conduction, electron had spin up, okay, and for some reason it flipped the spin, it cannot go back. Okay, this is spin forbidden. We must conserve the spin. Okay, the photon or the interaction of photon with magnetic field is extremely weak, and it will not flip the spin. Okay, and this is also happens in TMD, but in actually every material that spin flip is not allowed, and you can flip the spin with many different mechanisms. You can have exchange interaction, you can have interaction with the nucleus, whatever. Another kind of dark exciton is momentum forbidden. So if we have the relative electron and hole position in different place or different momenta, okay, we will not be able to emit light. You remember oscillator strengths tells something about psi at r equals 0. Okay, so the relative coordinate of the electron and hole also must be, or the relative momentum must be the same. Center of mass must be very small, the relative must be the same. Okay? Okay, and this is just an example what happens to the photoluminescence when we change temperature. Okay, and we see here two examples. In this example, and this is a bit annoying because here temperature goes up, and here down. Okay, but why? Because the dominant feature here is higher temperature and here is lower temperature. Okay, just visually, it's easier to look at it. So the left image is the photoluminescence of tungsten-based TMD. And tungsten-based TMD, the lowest excitonic state is actually dark exciton. Okay, so you can imagine that at low temperature, okay, if we excite the sample, most of the exciton will be in a dark state. They will not emit light. Some of them, by chance, will emit light because before they relax to the ground state, they will have the chance to emit light. Okay, from the bright state. Another thing is that the dark state, again, because we are in solid, it's a bit relaxed. So we also see emission from the dark state. It's weak. It's very, very weak. Okay, another thing that we have in these samples is, we'll talk about it later, but it's tryons. This is why we see more than two lines. So in tungsten-based materials, we have the bright exciton, the dark exciton, and tryons, a few kinds.
But if you have a dark state exciton, eventually it does give up its energy.
Usually with photon.
So it has to decay photons, just at a very slow rate.
Yeah. So
why? So this is a bit stupid, but if you're like, if you didn't normalize the PL, I don't know, like, you know, if you're accumulating, if you're launching the pulse and then accumulating all of the PL, eventually it will come up to the same.
No, but yeah, but once you have a lot of excitons, and you have exciton interactions, and then you can scatter them.
Mm.
So this is also, so you have a limited amount of density before you open new channels for emission. Yeah, so the idea here is that in low temperature you have very weak signal. Usually in a solid state, when you lower the temperature, you have higher intensity in photoluminescence. Photon plays a smaller role, and the peak is sharper because you don't have broadening due to phonons and temperature. Okay. However, with the tungsten-based material, because the cold temperature, the ground state is dark, when you increase temperature, you make the distribution between dark and bright more equal. So in higher temperature, you have equal distribution to be in bright states and dark states. Okay, so you get much more intensity actually when in room temperature than in cold temperature. The situation is opposite in molybdenum-based or material. And this is because in this case, the ground state is actually the bright exciton. Okay? And I will just mention, you see a large peak, and here it looks like you see that it becomes large again. This is not the case, just increase multiply the scale, that you will be able to see it. So it decreases until here, okay, and from here to here they just multiply the scale with different numbers. Okay, you still have emission in room temperature. Okay, and specifically in this,
I just want to comment that according to the Geneva Accords, this type of data manipulation should be illegal. Please don't do this at home.
yeah, correct. You also see here two peaks, one is trion, the other is exciton. We'll talk about trion. The lower energy is trion, actually. The larger peak here. It was a bad sample, I guess. A lot of defects. We see trions in PL when we have a lot of defects. Okay. So this is PL. You talked about valleys in graphene. Too much, I guess. And so we go back. I will not discuss this too much, but we'll go back to the first image or the first slide where we can see this valley description in K-space. Okay. And again, we will not talk about the B exciton, so we have the split here and the split here. Okay, in the valence and conduction band, we will not look on the lower energy. Okay, but what we'll do is we can see that due to the valley degree of freedom, okay, in the K valley, we can promote the electron from the conduction band to the valence band only with sigma plus light, right-hand circularly polarized light. In the K prime valley, we can only use sigma minus. Okay, so we have some correspondence between the light polarization to which value we excite. So in that sense, we have some probe to valley physics. Okay, it's direct probe. We can probe the K value without probing the K prime value, or opposite, using this optical excitation. Okay, usually if you want to do this in other experiment, you need to apply magnetic field, but magnetic field already changed what you are studying. Okay, but here you have direct probe to valley. Okay, so it's true for absorption and emission. So if we also look on emission, we can talk about value polarization. How much, if we excite electron from the conduction band to the valence band, how much time or how good we can say what is the value, what is the polarization. And we can see that usually it's not perfect. So usually we have scattering. We excite electron from the valence band to the conduction band. After some time, the electron will scatter. Okay? And now this depends. What is the initial energy that we use to excite? If we have high energy, usually we lose the valley polarization faster. Okay, we scatter from K to K prime. If we excite with lower energy, usually it stays longer time polarized. Okay, and this is kind of this experiment. Okay, when we excite here sigma plus, and we observe emission, sigma plus in black, sigma minus in red. So we have some valley polarization. It is not perfect. Okay, it's not zero in sigma minus. Okay, this is opposite picture, excite sigma minus. What is also important is what happens if you excite with superposition. Okay.
Linear.
Then?
So linear polarized light?
Yeah. So superposition of circular is linear polarized light. In this case, the excitation is H. H is just arbitrary in-plane axis in that sense, and V is the perpendicular to that. Okay? And we can see that we actually have similar signature. So it means that even if we excite superposition, we have equal distribution between the K and K prime, okay, with well-defined phase, because the light give you a phase of the excitation, okay, between the sigma plus and sigma minus, okay, and therefore between the K and K prime. So this phase remain. We don't lose the phase. So we can think about it. We can think about it as sigma plus and sigma minus, it's obvious. It's the eigenstate of the problem. But we still preserve the phase when we use superposition. Okay? And this is again with PL. It's matter of competition between how fast we scatter between the valleys to what is the lifetime. If we have materials or samples that are not clean, that scattering is faster, we will not necessarily see valley polarization at all. If we have very good and clean samples, and the lifetime is fast enough, we will see valley polarization. Okay, and this is really, people do it for more than 10 years now. It's still, you see it in some samples, you see it, some other you don't. Now we go to the fun part, which is
Not a break?
no, what is not fun. And this will be also the almost the last topic for today. And this is the interaction of the exciton with additional charge carriers. Okay, and we start with trion. And a trion is a bound state of exciton with another charge carrier, one charge carrier. For example, here in this illustration we have exciton, let's say, electron hole pair with additional electron. Instead of additional electron, we can also have additional hole. Okay, and in that case we also have binding. Okay, we have lower energy of the optical transition when we have additional charge carrier.
Because the screening is higher.
No, because so the optical transition is the transition. In this sense, you can think about it between you have electron and electron plus exciton. Okay, and when you have the exciton, the electron, the they actually reduce the energy. Okay, and this maybe the simplest way to think about it. I don't have an image, but think about the exciton as you have the hole and the electron. Okay, and this is the hole. And if you put the electron in the other side, so the Coulomb interaction of this electron with the hole is negative. Okay, the potential is negative, and with the electron is positive, but the electron sits closer to the hole. So overall, it has lower energy. Okay, so in this case, the two electrons are distributed in a way that the overall energy is lower. Okay, so this will be the eigenstate of this problem. So we have a bound electron and exciton state. Okay, and these trions can appear either in samples where we have impurities or local traps for electrons or holes, or when we dope the sample with gates. Okay, so if we just put more electrons to the sample, to one or two-dimensional sheet, these trions can also appear. However, we don't like trions. We like them, but not so much. So let's complicate the picture. And now let's assume that we don't have only one electron. So if we have one electron, the trion picture is good. We have a bound exciton and electron. But if we have many electrons, the picture is a bit different. Which electron interact with the exciton? It's a different question now. Okay, so for this problem, we actually we get a slightly different theory and arguments. Okay, and for that we call exciton polaron. So what happens? intuitively, we can think about exciton that moves in this Fermi sea of electrons. Okay? And once it moves, it pushes away the electrons. The electrons either want to come closer or farther apart for the exciton while it moves. So this is this picture. So when the exciton moves, it can either repel electrons or attract them. Okay? But it doesn't tell us which electron. It's not single electron. Or in another word, this exciton just makes polarization in the material. Okay? And this problem is also somewhat similar to a Polaron picture with photons, but it's not exactly because the electrons are fermions and not bosons. Okay, and the key idea is that when we have this Fermi sea of electrons, the exciton moves around and it can make or generate electron all pair in the Fermi sea. In this case, it will be intraband exciton. Okay, and what else we want maybe is to go to the limit when we have one electron. We want our description to still be valid. Okay, so we move from one electron to many electrons, but we still want one electron to be valid in this description. Okay, so this is the limit of zero doping, or zero electrons in the Fermi sea. Okay, another thing which is important is that this polaron, or this polarizability, polarization is neutral. Okay, it's not fermionic anymore. Okay, so the number, we don't change the number of particles in this state. Okay, and now we will come to the second Hamiltonian. Only the second. But before that, we will just describe wave function. Okay, and maybe in a few slides we'll go to the Hamiltonian. But the idea here is that we can try to guess a wave function, describe this kind of polarization in the material. Okay, so we have two parts of the wave function. We have this part, which is just an exciton. This is bare exciton that does not interact with the electrons. Okay, so and we have some probability to have it. Okay, and we have another part of the wave function, and in this part we just have exciton. Okay, that gives some momenta to the electrons. Okay, the exciton, and here we have just a creation and annihilation of electrons, but with different momenta. So we actually give excitation to one electron in the Fermi sea. We give him additional momenta or additional energy.
But you also get momenta.
Yeah,
Because you get
we
plus-
exchange momentum. Exchange the momentum between the exciton and the electrons in the Fermi sea. Okay, and we must remember in this case that if we have a band and we have at cold temperature we have electrons. Okay, we have all the electrons are until finite momentum, the Fermi momentum. Okay, so the exciton cannot give momenta which is larger than the Fermi momentum. It cannot generate all which have larger momentum than the Fermi momentum. So this is why the sum here, okay, is all the way. It's only below the Fermi momentum for Q, and above it, of course, you can have more. Not probable, but you can have more. Okay, which relates also to the momentum of the exciton, initial momentum. Okay, so what happens is that the exciton moves and generates electron all pair in the Fermi sea. Okay, a small excitation. I will have short cartoon for this later. What is also very
Sorry.
important
Electron hole pairs or in Fermi
In
scene,
the Fermi.
these are not excitons on their own?
Exactly.
Okay. Oh no. Is it excitons all the way down?
The exciton all the way down. Another very important consequence of this wave function is, even so it doesn't look for me here, it actually relates to the density of the electrons. Okay, why it relates to the density of the electrons? Because the Fermi momentum relates to the density. Okay, so, okay. Another thing that is maybe very, very important is that this part of the wave function does not interact with light too much. Oh, sorry, it does interact with light. This part is this is part described a trion state. It's a bound electron in the exciton state, and this part is a bare exciton. Okay, so we can see that if we increase the density and these parts become more important than this part, okay, so the bare exciton state will have lower probability, we'll have lower probability to see it, and the trion or polaron state will have higher probability to see it with density. Okay, or in other words, this KF, the summation goal, you have more states to sum over.
This is very similar to the phonon scattering situation we had with the EBG temperature.
Okay. And this is what we discussed. And so just to make it visual, so this is the wave function, which is, we call it the Chevy ansatz. Okay, this is a trial function. And this, we can use this function actually to minimize this Hamiltonian. And the Hamiltonian here is made out of, it's simple, usually it's more complicated, but this is the base. The exciton energy, electron energy, okay, and interaction term between the electron and the excitons. Okay? So we use this wave function, we calculate the energy or the and minimize here the parameters. Okay, so this is a trial wave function that works pretty well. Okay, and if we talk about the visual interpretation of this wave function, we can generate electron hole pair. Okay, obviously if we have some Fermi C, we cannot generate the electron in the conduction band at the bottom. We must add it on top of the Fermi C. Okay, so this is why we have here Ex of Q. Okay, it's some limiting factor, so the absorption must come on top of the Fermi C. Okay, it's not true for photoluminescence, by the way. And then, so this is the part of the bare exciton that we have here. Then the other part of is the generation of electron hole pair on the Fermi C. So we take one electron from the Fermi C, we excite it on top of the Fermi C with some finite momenta, and we leave a hole in the Fermi C. Okay, and this is here the second part. Here we have the exciton to the left, but with electron hole pair. Okay, and the hole here, the green hole, is actually also in the conduction band. Okay, so when the exciton moves, it just generates these fluctuations in the Fermi C, over the Fermi C. And this is let's keep it as basic as it is, and obviously there is much more physics about it. This is also how people treat impurities in cold atoms. Okay, it took quite some time to take this picture from cold atoms to solid state physics. So until lately, people just talked about ions. The last slide. Okay, and now just an example of how absorption or reflection looks like when you change the electron density in the material. Okay, and this need to follow this wave function that we just described of the Hamiltonian. And so here in x-axis, obviously that we have the energy. The y-axis, even so it's gate voltage, it's actually electron density. Okay, equivalent to electron density. Between these two green lines, we have the Fermi energy is in the gap. Okay, so the chemical potential is in the gap. Okay, so we don't have any additional electron or all in the sampling. Once we start dope the sample, now we can see two branches that we have seen before. So we said that we have one branch that get attracted, which is similar to trion, to the bound state, and one which get repulsive. Okay? And this is what we see here. We see that the exciton that we have seen before now is getting blue shifted. It means that it has lower energy. Now, okay, so it repels the electrons around it. Okay, and then we also see new resonance, which is in very low densities. We said it's similar to trion. Okay, bound exciton and electron. But when we have higher densities, it must go to excitations in the Fermi state. And this we can see from the other side. Okay, because we have also the repulsive branch. Okay, so if we just talk about trions, we should not see the repulsive branch. Okay, once we have additional electron, we just need to see attractive branch. Okay, so this is electron doping. So attractive polaron, repulsive polaron. This is similar to the trion, and this is similar to the exciton. Okay, we have two parts of the wave function. The same happens even so with different slope when we dope with holes. It's a bit more difficult to see. Here we have this blue shift of the exciton and another branch for the attractive polaron. Now with this, we go to a point where we can say, okay, we have some electrons in the sample. We have some interaction of excitons with these electrons. Maybe we can study something about the electrons that lives in the sample. If the electrons do something special, there are some quantities that we can measure. Not all, but some quantities that we can measure. So we can, for example, measure incompressibility, or if there is some gaps when we dope, okay, or in the spectrum of the electronic states. Okay, these kind of things we can measure. We can also measure ordering of electrons if we do it correctly, that regime. So there are many options are open due to this very simple picture that excitons interact with electrons. Okay, and we can also think about the opposite. Okay, how we can change the excitons using the electrons. Okay. So I guess because Hanan is tired, I have.
No, if you don't want to eat, you don't have to.
No, but this is more or less the other half. This is only the first half of what I prepared. But the other half, let's keep for next year. Hopefully, all of you will still be here on the same place next year. Yeah. So let's conclude with that.
Thank you very much.